So I think we left off last time with the expression that the velocity is equal to the change in position over the change in time, that the acceleration is the change in velocity with respect or over divided by the change in time. And then we solved those two together to come up with our old friend that VdV is equal to ADS. You remember that from last time? Okay. So what I'd like to do is look at each one of those three essentially equations, one equation, two equations, and three equations, and see if we can come up with some kinematics equations for those. I'm not sure you went through this process in physics, but I'm quite certain that you probably used the equations that we're going to come up with. So if I take our friend VdV is equal to ADS and essentially integrate both sides of this, so taking equation number 3 and integrating both sides of this, integrating VdV over from V1 to V2 and ADS from S1 to S2, I'll come up with something like this. I'm going to come up with V2 squared minus V1 squared divided by 2 is equal to then the integral of A ds with the limits of S1 and S2. Now I made good progress on the left-hand side. I didn't get very far on the right-hand side, but I can make good progress on the right-hand side if I'm willing to commit to something, and that is to say that if I have constant acceleration. So if the acceleration is equal to a constant, of course I can pull it out of the integral like you could pull any constant out of an integral, and we could continue on. In doing that, we would get that V2 squared minus V1 squared divided by 2 is equal to A times essentially delta S, right? So A times delta S, where this would be S2 minus S1. And if I rearrange this a little bit, we can get the form that you've probably seen before. That is V2 squared is equal to V1 squared plus 2 times A times delta S. And I suspect you've seen that in physics. Did you see that in physics? Okay, that was the kinematics equation. And probably more important than remembering that equation is to remember the stipulation for that equation, that the acceleration has to be constant. There's lots of good problems where acceleration is constant. Free fall problems, the acceleration is constant. If you're going down the racetrack with an acceleration that's a fixed value, you have constant acceleration. But there are a lot of problems that do not have constant acceleration, so you have to be careful of that. If you don't have constant acceleration, you're going to have to go back to these rather ugly expressions here and work out the calculus on it. That's where a lot of people, they try and bend the rules and try and apply these kinematics equations to something that has non-constant acceleration. So remember, if you have constant acceleration, by all means, use these easier equations. If you don't have constant acceleration, don't try and fit something to something that won't work. You're going to have to go back to the base equations that we see here at the top of the page. Questions with that so far? Well, let's hang on to this one and go on to an example, a free fall example. So if we look at a free fall here, so I take some coordinate system and I have this body above some plane, so we have some plane here. Just like if I were to raise something above this surface here and allow it to fall back to that surface, I'd like to find the impact velocity, the velocity at 2 where this pen were to come down and to hit that page. Okay, so there's a few things that we're going to do with this. I'm going to take the direction up as positive. So that means that if I have the gravity here acting down, and a lot of times I put acceleration in as a double arrow, so I'll put my acceleration acting down, so I'm going to say that acceleration A is equal to minus g, because I'm going to take positive up in this problem. I'm also going to have the height then going from 0 to h, so we're going to start out at some distance h above the surface. And this is important to document because, I mean, we could say that this was the initial point, that this was 0, and then this was minus h as it fell down. But taking positive up, we're going to go from 0 to h. Of course, by definition of free fall, I'm not throwing this thing down. I'm taking this pen here, and I'm simply letting it drop. I'm simply letting it fall back towards the center of the Earth. I'm not actively throwing it down, so my velocity v1 is equal to 0. I'm just releasing it. I'm not throwing it down with some initial velocity. So what I'd like to do is I'd like to find this velocity 2 here. What is the velocity at 2? Well, we have constant acceleration, don't we? This is, of course, a constant. So this is a good use of our kinematics equation that v2 that we just talked about, v2 squared, is equal to v1 squared plus 2 times a times delta s. So if I go through this thing then, v1, we agreed that that was 0. I was just releasing this. I was just dropping it. So I can say then that v2 squared is equal to 2 times minus g, that was our acceleration, times our, we're going to go from what, 0 to h, or s2 is 0. This would be s2, and this would be s1. We're starting at the upper surface, so there's s2 is 0, and then I have to subtract s1, that's h. So I come up with this being equal to 2 times g times h. Or I could say then that v2 is equal to the square root of 2 times g times h. Okay. And a lot of times if you're less careful with the signs, you'll end up having a positive value on the h and maybe a positive value on the g, and it works out for you. That would essentially be taking positive down, and that's okay. But I tried to be more careful and more rigorous with my signs here. So this is our expression. Our impact velocity would be equal to the square root of 2gh. Let's look at the units on this. Looking at the units on this, I would have the square root of, in English units, 2 of course doesn't have any units, but g would be feet per second squared, and h would be feet. So I end up then with the square root of feet squared over second squared, which would give me feet per second, or a reasonable velocity in the English system. You could make the same analysis in the metric system. You know, some people might be wondering, well, why do they have to take this dynamics class and whatnot? So I'll put this in a little bit of context. You'll see this again. Those of you that go into fluids problems, if you look at a chamber full of fluid, so we have fluid in here, and I realize you probably can't see color very well, but we'll color this a nice blue fluid in here. The velocity that this comes out, this velocity is going to be a function of the height. In fluids, we're going to call that the fluid head. The higher that is, the more velocity we will have. And the expression is going to look really very much like this expression here that we came up with. And you've probably seen this before. You could demonstrate this to yourself. If you take a tin can and fill it up with water, and then put a hole here, the fluid tends to come shooting out like that. And as you have the holes increase in height, so you have less and less head pressure, so to speak, the fluid comes out like that. You can choose to put the holes in however you want. It's kind of fun to fill it up and shoot them in. Anyway, you've probably seen that. So this distance above here, this height or this head, is important in coming up with the velocity that this comes out with. So you'll see these calculations again, even if you go into fluids and things like that. Questions with free fall? So the key here, of course, is that the acceleration is equal to a constant. If we didn't have that, we couldn't use this. We'll move on then if there's no questions. I'd like to, we looked at VdV is equal to AdS, so we haven't looked at A is equal to dV dt, or for that matter, V is equal to ds dt. So I'd like to exhaust this discussion by looking at those two. So looking first at A equals dV dt, I rearrange that a little bit here. I guess essentially cross multiplying, so dV is equal to A dt. And then if I integrate both sides, so I'm going to integrate dV from v naught to v of t. V sub t probably would be a better way to say that. And then I'm going to integrate A dt from 0 to t, time starting at 0. So when I go through and do that, this comes up as v sub t minus v naught is equal to the integral from 0 to t of a dt. And again, we made some progress on the left-hand side, but didn't get very far on the right-hand side. So what we could do then is make a concession that if a is equal to a constant, okay, if a is equal to a constant, I can bring it out of the integral, right? So that allows me then to say that v sub t minus v naught is equal to a, essentially delta t, where delta t would be a t minus 0, or maybe in a little more general form, t2 minus t1. Okay. Well, if I tidy this up a little bit, I could say that v at some time t is equal to my initial velocity v naught plus a delta t. Okay. Do the units work on that? If you took an acceleration unit and multiplied it by time, so let's say that we take feet per second squared and we multiply this by seconds, do I come up with velocity units? I do, don't I? Feet per second. So that equation looks good from a unit standpoint. And I think you've probably seen this equation before. I don't know if you derived it in physics, but I suspect you used it in physics, didn't you? Have you seen that one before? Good. Okay, so another kinematics equation, but probably more important than deriving this equation or remembering it or maybe even using it is understanding that it has a very limited constraint, that the acceleration has to be equal to a constant. There are a lot of good problems. We just got done with one, free fall, where acceleration is constant. But don't try and force this into something where the acceleration is not constant. We ready to move on to the last one? V is equal to ds dt. Okay? So if I cross multiply on that and rearrange it, I get ds is equal to v dt. So I'm looking right here. And I'd like to make my substitution for v. We saw just a moment ago that we can make a substitution for that. We could say that that's really equal to v naught plus a delta t, or I think I'll just say at. Okay, that's going back and using this equation here that we just developed. So I could say then that I have that ds is equal to v naught plus a t dt. And now I'd like to integrate both sides of that. So I have the integral from s naught to, let's say, s of t or s sub t of ds is equal to the integral from 0 to t of v naught plus a t dt. Okay. So what are we going to come up here with on the left-hand side? We're going to have s sub t minus s naught is equal to, and then on the right-hand side, I think we can do that. We're going to come up with v naught t plus minus 0, of course, for the lower limit, plus a t squared over 2, evaluated at 0 and t. And put that t back in, of course, put the 0 back in. But put those limits in and rearrange this. I'm going to come up with s at some time t, sometime later, is equal to then s naught, moving that to the other side, plus v naught t plus 1/2 a t squared. And I suspect you definitely saw that in physics. I don't know whether you derived it or not. But, did you use that one in physics? Yeah, that's a real classic one. Do the units work on that? Each term should have units of position, right? So if we look at the units here, this is, of course, in an English system, this would be feet, this would be feet. If I take velocity, feet per second, and multiply it by time of seconds, I get feet. And a half doesn't have any units, but acceleration, that would be feet per second squared, and I multiply it by seconds squared, again, I get feet. So the units work out on each and every term there. Now, we didn't implicitly come along and say if a is equal to a constant, but what was used to make this substitution? Yeah, refer back over to here, right? So A has to equal a constant. That's where we got this one from. So that carries over with that. Just because we didn't say it doesn't mean that it doesn't exist. So these kinematics equations, they're powerful, they're handy, they're easy to use, but they are limited in terms of the acceleration has to be equal to a constant. So questions with that? So we've got those equations, and we're going to get some practice using those. The question comes up is, what if A is not a constant? What can you do? Well, you just have to go back to the basic definitions. You have to go back to V is equal to ds dt. You can say that A is equal to dv dt. You can put those two together if you want, combining these, and say that v dv is equal to A ds. That's about as good as you can get. You put your expression for acceleration in there and try and sort it out. So when we get together in the next lecture, we're going to talk about some problems like this where A is not a constant and go through those. And then we'll come back and we'll get to use our kinematics equations where A is a constant. And one place where A is a constant is oftentimes in projectile motion. Certainly in the downward direction, we look at A being equal to a constant. That's the acceleration, right? And we're going to try and keep life really easy and talk about the acceleration in this direction, that A is equal to 0. We're going to neglect air drag. And we're going to say that that projectile is not slowing down in the horizontal direction. And I'd like to start this subject. We'll be getting into this probably not, well, maybe towards the end of next lecture, but certainly the lecture after that. But I'd like to get you to thinking about projectile motion. And I'd like to do a little experiment here where if we were to fire a projectile out of this gun, this rifle, and at the same time we fire that projectile out, we drop a projectile like that. And the question comes up is if the line of sight of our rifle is absolutely parallel to the ground. So maybe we go out to Utah and the Great Salt Flats. We've got this very flat surface down here, and we set up the line of sight of our rifle so that these two are absolutely parallel. They are perpendicular to a mutual line. And we fire this thing off. I think you can imagine that this projectile is going to come down here, and it's going to drop and eventually hit the salt flat someplace downrange, right? Anyone that's maybe done this, even if you've never shot a rifle, you've thrown something, you recognize that it has drop. It would be unintuitive to think that you could throw a baseball or a tennis ball and have it go straight forever, right? That'd be kind of cool, but that's not the case. So that one's going to come down there, and of course if you drop this one at the exact same time, it's going to fall. We just got done talking about free fall. That's again a pretty easy demonstration right here. Okay, people get a little more nervous if we brought in a rifle and tried to do the other part of this demonstration. Although they have some neat stuff in the physics department that does this, that fires a projectile with a spring and drops one at the same time. But anyway, I think we can do this as a thought experiment. When are those going to touch the ground in relationship to each other? At the exact same time. Yeah, you've talked about this in physics. You've learned the lessons well, that this projectile here hits the ground at exactly the same time this projectile does. Okay? And this leads then to classic problems like bank robbers jumping from building to building and hunters trying to shoot monkeys out of trees as they drop down. We'll talk about some problems like that, and you've got some problems like that in your homework. But the premise behind this is that horizontal velocity is independent of vertical velocity. Okay? They're happening at the same time, but they're independent. And really the only way that we can tie them together is with time. Okay? So we'll look at the horizontal motion separately from the vertical motion and really only tie those together in that they are happening at the same time. So give some thought to that little thought experiment and hopefully verify in your own mind that horizontal velocity is independent of vertical velocity. So like I mentioned, where we are going to go in the next lecture is we're going to tackle some problems where A is not a constant, That'll give us a good chance to brush up on our integration and our calculus and things like that. And then we're going to get to use those kinematics equations, and we're going to use them in projectile motion. We'll come up with some kind of cool projectile equations and things like that where acceleration is usually fairly constant. So that's where we'll go.